Hi, this is Anshu and I am back with a new topic called as a stochastic process. In this session, I'll be discussing basic concepts of stochastic process, when a process is called a stochastic process, classification of stochastic processes, basically stochastic processes of different types, counting process, stationary, independent and renewal process. So let's start with this basic definition of a stochastic process. What is called as when a process is called a stochastic process, or what is the relationship of a stochastic process with a random variable. Stochastic process is nothing but a process when you start considering time as a parameter when deriving a random variable. We can say that in probability theory, stochastic process is also named as a random process. Okay, and it's nothing but a collection of random variable which includes time as a parameter. Here, this process represents the evolution of random variable over time. We can also say that stochastic process is a probabilistic theory. Stochastic process contains some sort of indeterminacy in it. That means even if you know the initial condition, but still the process can evolve in several, or we can say infinitely many directions. Actually, in probabilistic theory, stochastic process is a counterpart of a deterministic process. The basic definition of a stochastic process will be, the actual definition will be xt, where t belongs to t. This is actually a definition of stochastic process. So here, stochastic process is nothing but a family of random variable which is defined on a given probability space, suppose S, and is indexed by a parameter t, which is also called as t parameter, and it varies over an index set t. This is the formal definition of a stochastic process. So, in short, or to make it further clear, we can say that stochastic process deals with the dynamics of probability. When we enlarge the concept of random variable from probability space or sample space S to a parameter t, that is, we start including time in deriving a random variable, then the process which we get is called as a stochastic process. Here, let's consider a random variable x which is defined over a sample space S. So if you say xs, where your S belongs to capital S is a sample space. Now you have considered a parameter t. So your process, this will become S comma t. So this is a function, this is a random variable function considering t, and it is defined over sample space S. So this is nothing but a stochastic process, a formal definition of a stochastic process. Now your random variable is mapped, or you can say the event is mapped to different numbers at different times. So if your t varies, with this constant S, you get different values of random variable. Okay. Now you have a xst as a random variable function, is stochastic process. Now you can have a condition where you can either fix S or you can fix t. For example, if you fix t, what you get is x S. If you are fixing sample space S, you get x comma t. So now you have a fixed S, that is your sample space S is fixed, and now your t varies. Okay, so here xts can be viewed as a collection of time variable functions. Now this will become like this. You can say that xts is a collection of functions over time. Now similarly, what we can do is we can fix t. So what you get is xs. Okay, this is nothing but a random variable. So now at constant t you get a one value which is just a random variable. So in other terms, what we can say is that a stochastic process will become a random variable if stochastic process is transformed to a random variable if your time parameter is fixed. Okay. So it will be something like xts transformed to xs. Okay, your time is fixed, just stochastic process gets converted into a random variable. Here xts, or the formal definition xts becomes xs. It's just a formal definition of a random variable. Now here based on the probability space and the type of probability space, we can have different types of stochastic processes. So now values xt, so the values of this random variable are called states. This is called states. Okay, and the set of all these states constitute a state space of the process. So this collection of xt, collection of xt is probability space of process. Okay, so your xt is nothing, and the values of xt is the states, collection of states converts to probability space of process. So now based on the probability space, the type of probability space, and what we have is this sorry, you have a t index set I. So you have a probability sample space as discrete. You have a continuous. Okay. So here what you get is your index set I. Okay. Based on that, so again you have discrete time. Okay, and you have continuous time. Continuous time. Now the probability sample space. So you have a discrete state process. Discrete state. Here you have a continuous discrete time. Discrete time, continuous space. Here you have continuous time, discrete space, and here you have a continuous time and continuous space. So based on the sample space, you have a n parameter t. You have a discrete time, discrete state process, discrete time, continuous space process, continuous time, discrete space process, and continuous time, continuous state process. Now the conditions when the stochastic process gets converted into four types of processes. So here we will say like this. If a state space of process is discrete, state space we have defined by S. If this is constant, sorry, this is a discrete, then you have a discrete time discrete state. Okay, this is, if your state space is continuous, this is continuous, then you have a discrete time continuous space. Now if you have a fixed parameter t, like the discrete values of time, okay, then you have discrete time continuous space, and you, if this t is continuous, you have continuous time continuous space. Now if you have a t as a continuous but s as a discrete, okay, your sample space is discrete, so you have continuous time discrete space. Reverse, if your time is continuous and your s is discrete, sorry, t is discrete, s is continuous, then you have discrete time continuous space. Now let's say that random variable is a function which is defined on some sample space S. Okay. Now we are performing some experiment. So the family of random variable, okay, that will be, you can say, defined as x t comma s, where s belongs to s and t belongs to t. Okay, so let this be a family of functions. Now if you fix t, so let's say t is equal to t1. So now what we get is x t1s, sorry, x t1s is equal to x t1s. Okay, so this is a random variable which is denoted. Now here s is varying over sample space A. Now if we consider another sample point, let's say t is equal to t2. Now again, what will be the function? It will be x t2 s is equal to x t2 comma s. This will be the function at another sample space. So we can say that if you have a fixed sample point s, so x s1 t is x t s1. Similarly at t2. So when both s and t varies, now if you vary s and t both, if these both are varying, then we get a family of random variables. What you get? Varies. You get family of random variables. So this family itself constitutes a stochastic process. This is how you define a stochastic process. Now we have different types of stochastic processes. We can say that a stochastic process can be again defined, classified into different types. But before going into that, I would like to discuss something on the relationship of a stochastic process and a sample variable and random variable. So how we will define it is, you draw this, you have this. Suppose this is one sample point, random variable s2, s1, s2 and s3. Now t is equal to t1. Okay. Now these are the functions. Okay, so let's say it's something like this. So this is x s1 t s1. Now for this we have something like this. So what you can say is x t s2, and here you say something like this. It can be any function, it's just a random thing. So you have x t s3. So if you say t is equal to t1, so x t1 is a random variable. So what you can say is this is stochastic process versus random variable. So this becomes a random variable. This is nothing but a random variable. This is how you diagrammatically represent the relationship of a stochastic process to a random variable. Now, starting with the classification of a stochastic process. In many places, I will be using the short form SP. SP stands for stochastic process. Now, before going into the details of different types of a stochastic process, the basic definition will be, let's say, T is equal to T1. This is fixed. Okay. So now, X T1. This is a random variable. Okay. Now, this defines the state of a process at time T1. Now, suppose for fixed x1 some fixed number. Okay. Here, the probability of an event, say x T1 less than equal to x1. Okay. So what will be the CDF of random variable xt1? So CDF of xt1. So the CDF for xt1 will be defined by x1 t1 is equal to fx t1 x1 is equal to probability of xt1 less than equal to x1. This is called CDF of xt1. This is also called as a first order distribution of process. This is called first order distribution of process xt1 such that t greater than equal to 0. Okay. Now we can modify it such that it becomes a second order function. So now till now we have considered only one time instant t1. If we consider two fixed instants, say t is equal to t1 and t is equal to t2, t1 and t2, these are the 2 points. So the xt1 and xt1 and xt2, these two are the random variables. If we consider the previous equation, so based on the previous equation, the second order distribution of the process can be easily figured out. So what will be the process? It will be f x1 x2. Again, x1 and x2 are two fixed numbers. Then t1 comma t2. What it will be? We will define it as f p xt1 less than equal to x1, xt2 less than equal to x2. Okay. This is called as a second order distribution function and is a joint PDF. Now let's convert it into nth form. So t1, t2 to tn, we have n instance. So what will be the nth order? So f xt, what it will become? So just like we have a distribution for two instances extended to n instances, p xt1 less than equal to x1, xt2 less than equal to x2 to xtn less than equal to xi. This will be the nth distribution. This is the nth degree distribution function. Okay, so this here we are considering that this x is equal to x1, x2 to xn, which all belongs to S, or you can say R, whatever it is, and your t is equal to t1, t2 to tn, all belongs to capital T. This is a parameter. So your nth order function will be used to define the other stochastic processes. So let's say that we are going to define first independent process. Independent stochastic process. So how it's defined? Till now the stochastic process, what is stochastic process, is defined as xt such that t belongs to t. So if the what will be the nth distribution function of this? So the nth distribution function from the previous probability theory, it will be fxt is equal to product of fx I ti, I is equal to 1 to n. Then what it will be? It will be nothing. I is equal to 1 to n probability of x ti less than equal to xi. From the independent stochastic process, that is the probability or the function or the distribution function is nothing but the product of the probabilities of independent random variables or independent functions. This is nothing but an independent stochastic process. The other important process is a counting process. Counting stochastic process.